Now for the synthesis of aldehydes and ketones, you will see as we are going through, you have done a lot of them before. Let's start from alkenes, okay? And in alkenes, you've done this by taking an alkene and cleaving it with ozone, okay? And so when you take an alkene which is substituted, then you get ketone. If it is not completely substituted, then you get an aldehyde, okay? So that's how it works. Now the ozone, the two reactions that I've given you here, they're both very similar except for the workup reagents. The workup reagents are slightly different. So if you see these two different kind of things going on with ozone, don't be worried, it's just a workup reagent, okay? Your key reagent for carrying out this reaction is ozone, okay? So the reaction will still be the same, which means the products will still be the same. So you get aldehydes and ketones. Here is an example of how this works. So if you have something like this, in which the alkene here is completely not substituted, it's all hydrogens, then you get a ketone over here and formaldehyde, okay, over here. So if there was more carbons here, then you would get a more substituted aldehyde. That's all. So ozonolysis is by using alkyne. The next synthesis is from alkynes, and in alkynes you have two kinds of alkynes, terminal alkyne and internal alkyne. So this example that is given to you here is for terminal alkyne. So if you have a terminal alkyne and you use mercury sulfate along with sulfuric acid, then you end up getting a ketone. Okay, a ketone, which means that your functional group is coming on the internal carbon. If you use borate along with hydrogen peroxide, then you will get an aldehyde, which means now your carbonyl is going on the outer carbon or the terminal carbon. Okay, and so you get two different kinds of products depending on what kind of reagents you use. So mercury sulfate will give you internal groups, whereas hydroboration will give you an aldehyde or a terminal group. This reaction is very similar to what you did back in the alkenes reaction for hydration. If you just use the mercury reagent and treat it with alkene, you will get Markovnikov addition and you get internal alcohol. And if you do a hydroboration of an alkene, of a terminal alkene, then you end up getting alcohol as a primary alcohol, or you would get the anti-Markovnikov product. This is kind of similar to that, okay? So which means that the mercury reagent is still giving you what we call the Markovnikov product, and the hydroboration is giving you the anti-Markovnikov product. So the functional group goes on the carbon with more hydrogen. Okay, that is anti-Markovnikov product. If you have internal alkynes, then you will only get ketones because internal alkynes have no hydrogens on them. So if there is no hydrogens on them, then hydroboration and mercury sulfate will give you the same product, which is a ketone. There is no option for an aldehyde. Aldehydes are also terminal groups, so you can't get aldehydes inside. Okay, you have to have that on the terminal group. Synthesis from benzene, this one is not that far off. We just finished doing this, and so you could use Fieldcraft acylation, and this is a synthesis of acetophenone. Okay, to make ketones, you can use any kind of acyl chloride. This one is acetyl chloride, but you can use any kind of acyl chloride to get whatever number of carbons you want over here. The only key thing is that the ketone will be attached to the benzene ring. Okay, that's what's going to happen. That's the only kind of ketone you can make from Fieldcraft acylation, but that is a synthesis of ketones. To make aldehydes, so for example, to make benzaldehyde, we use what is called the Garum-Koch synthesis, and the Garum-Koch synthesis involves the same kind of a thing, okay, which means you still have an acyl chloride, except that acyl chloride that you're generating is coming from carbon monoxide and HCl. Okay, so you end up getting something like HOCl, all right, except that you don't write it like that because it's generated in situ. In situ means within the reaction. So within the reaction, you generate the HOCl, the chloride, the acyl chloride by using carbon monoxide and hydrochloric acid. So, and then of course you have to use the catalyst, okay, in both cases. But anyhow, so you can make benzaldehyde using the Garum-Koch synthesis. I would prefer it if you remember these reagents. Okay, that would be much nicer than remembering it as HCOCl or HCOCl. You know, it's just not a good practice. Okay, it's good to know what you're really getting your reactant from. You can also synthesize aldehydes and ketones using oxidation reduction. And so here is the scheme that we usually talk about in oxidation reduction. You've seen this before in alcohols. So you can take a primary alcohol and oxidize it to aldehyde and all the way to carboxylic acid. That is what you have done so far. You can also take a carboxylic acid and reduce it all the way to alcohol. That is what you have done so far. Now we're going to go to aldehyde, okay, which is in the middle. So aldehydes and ketones are in the middle over here, which means to prevent an alcohol going to carboxylic acid, which is the highest oxidized functional group, you have to use a weak oxidizing agent so it doesn't go all the way through. When you're using a reducing agent, which means if you're going backward to the alcohol, to go from a carboxylic acid to an aldehyde, you would use a weak reducing agent. If you use a strong one, it will take you all the way back to an alcohol. All right. This scheme right here is shown only for a primary alcohol, and it is shown for primary because for secondary alcohols, you cannot take it to carboxylic acid. All right. And that's why this is only given for primary. Anyhow, here is the oxidation for primary and secondary alcohols. So if you have a primary alcohol, it will give you aldehyde as shown over here. Again, you use a weak oxidizing agent like PCC, pyridinium chlorochromate. If you have a secondary alcohol, now you can use a weak or a strong oxidizing agent that will take you to ketone. All right, so strong oxidizing agents are sodium dichromate, chromic acid, or you can also use potassium permanganate. All of those will give you ketones. Remember, secondary alcohols are internal groups, and so are ketones. Primary alcohols are terminal groups, so they will give you aldehydes. Again, primary alcohols use a weak oxidizing agent. Now for the reduction, you don't want to use a strong reducing agent. Remember that, okay? You want to use a weak reducing agents. The compounds that you use for reducing are not exactly acid. They're going to be acid chlorides and esters. When we get to the carboxylic acid chapter, then we'll talk about why you cannot use the strong reducing agents directly on the acid. Okay, so usually the acid has to be converted into the acyl chloride or to the ester before you can actually reduce it. Okay, so this is an added extra step. We will do this again when we get to the acid chapter, but it's a little bit of a preview for you. So I use a weak reducing agent, again a weak one, so that you don't go all the way to the primary alcohol. A weak reducing agent is given to you right here, DIBA. So it's written like this, which is diisobutyl aluminum hydride. So this is the isobutyl groups over here, aluminum hydride. Okay, so it can be written this way. This is the short form for it, and this is a long form. Okay, this is the actual reagent. So you should be able to recognize all of these, okay, that these are all reducing agents. That's what they are, okay? You're looking for the active hydrogen. You can also use sodium borohydride. You can also use dibal, okay, which is diisobutyl aluminum hydride, dibal instead of diba, okay? They can be written both ways. And the only one you do not want to use is lithium aluminum hydride, LiAlH4, because that is a very strong reducing agent. It will take it all the way to alcohol. So you don't want to use that. You want to use these ones, okay, or sodium borohydride. So then the other part about reducing agents is that, or this process here for the reduction, is that only aldehydes can be made this way because ketones are found in the middle. Okay, so acid chlorides and esters, they are both terminal groups. So which means you can only make aldehydes. You can't really make ketones, okay, using reduction process. So here is the first reaction here is for acyl chlorides. The way you make acyl chlorides, you take carboxylic acid, treat that with anyl chloride, get the acyl chloride, and then you can do the reduction on it to give the aldehyde. And here is one for ester. Okay, again you use the reducing agent diba, and then you end up getting an aldehyde. All right, really fairly good synthesis yields that you get for this one. Okay, so your oxidation reduction, be careful as to what reagents you use and what you're starting with. So now for some new synthesis. All the other ones that we just did until 4, they were all old things that you've done before in different chapters. And now this is a new one because this one is from Organometallics. Okay, and so you know the reagents already, you just don't know how to use them to make a ketone. Okay, so for example, organometallics, the two that you know are Grignard reagent, and then we also have what we call the dialkyl cuprate reagent. All right, and so you can use lithium reagents or Grignard reagents. Okay, both of those you can use them to form ketones like this. Okay, so for example, right here you start with an acid, you treat them with the organolithium reagent or a Grignard reagent, and then you end up getting a ketone. All right, so very, very simple reaction here. And here is the one, if you use dialkyl cuprate reagent. The way you make the dialkyl cuprate reagent is starting from this compound, which is a lithium, alkyl lithium compound. Okay, you treat that with copper iodide. The way you make this, by the way, is from alkyl halide and lithium. Okay, just like you made it before with the Grignard reagent. Treat that with copper iodide and you end up getting this reagent, and this reagent is actually very tame. Grignard reagents are very strong and organolithium reagents are very reactive, so you have to be careful when you're using these reagents. Grignards are better than organolithium, and then cuprate reagents are even more tame, okay, which means that you can really control your reaction, okay, this way. So taking this reagent and treating it with acyl chloride, this is the leaving group right here, and here is your nucleophile, and so it's like a nucleophilic substitution, okay, that you get. So very easy to do. This is exactly kind of what you're doing here. Your leaving group here is OH, okay, that's all. So it's a substitution reaction in both cases. And then we can also get ketones from nitriles. Now remember, nitriles are CN groups, which we call cyanides when we were in Gen Chem, but now that we are in organic, we call them nitriles, okay, when they're connected to organic compounds. So if you take any kind of a Grignard reagent, treat that with a nitrile, any kind of a nitrile, whether it's a cyclic or it is aliphatic, it doesn't matter. This is the intermediate you get on hydrolysis, you will end up getting a ketone. So whatever was on the Grignard reagent and the carbon stay connected. Okay, that's the new bond that is formed. After hydrolysis, you get the carbonyl. The carbonyl is coming from this carbon, whereas the CH2CH3, the ethyl group, is coming from the Grignard reagent. Okay, so if you keep that in mind, then you will not lose any of your carbons in the process. The nitrogen has gone away. As you can see, it bonds with the Grignard reagent. So nitrogen goes off over here, and then oxygen is coming from water. So this is it as far as the synthesis of aldehydes and ketones are concerned. You only have two new syntheses to work with. Otherwise, all the other syntheses are old for you. Alkenes, alkynes, benzene, and oxidation of alcohols. These were kind of a review. So these two here then are the new synthesis for you. Grignards and reduction of acyl chlorides and esters.